Welcome back to the Decode Podcast booth, Apex 2026. We are joined by Bob Bouchard, and he is with BTU. He is currently the Director of Sales in the Americas. We got to get that in there.
That's right.
But I understand that you've got kind of a long and storied career with BTU, and your origins within the company aren't necessarily on the sales side of things, but actually conceiving and engineering the products that BTU offers.
Yeah, that's true. When I started with BTU, I'm working on 36 plus years with the company, so I've kind of seen it all. But in particular, the SMT products in particular is where I really cut my teeth in terms of getting into the product management side of things. So define the products, the features, what we needed to bring to market. That was a really fun part of the career, being exposed to it. So really helped the transition going into sales because I know the products inside out. So
I don't know if this is just my perception and if it's inaccurate, but I feel like reflow is something that kind of gets overlooked, right? People look at placement and the screen printing process, and there's so much attention that's focused there that maybe sometimes reflow feels like the left out entity.
It's the most forgiving, right? So if you don't have paste there on your pad, right, it's not doesn't matter what you place or how, right? So, but your reflow, I feel like you can have this bigger process window than you can with any of the other ones, right? Like pick and place on the small component can't be off by much, right? But it's a lot more forgiving,
That's starting to become challenged, though, right? I mean, we were talking yesterday in the booth about how specific some of these component reflow profiles are, right? So maybe that's been true historically and is changing now. Would you agree with that statement?
Yeah, I mean, the way I look at it, the way we look at it at BTU is, as you pointed out, the focus is on some of those critical placement, screen printing, right, AOI, these high values areas. But we look at it as, but you're going to add all the value. After adding all that value, you're going to put it through an oven at the very end. Are you sure you really want to put it through just any oven? I mean, this entire process all comes down to the end at reflow. So from our perspective, it needs to be as precise as any other part of the process.
Yeah, I mean, it's a critical part, right? It doesn't matter how good your perfectly stable your print process is or your placement. If you don't have a good reflow profile, if your oven isn't actually hitting the set points, if it's not calibrated right or whatever, you're not going to get a good, high reliable product. Even if frequently people get boards that are aesthetically pleasing to the eye and the joint, the way the joints appear, right? But there's so much hidden complexity to the way those joints are formed.
I experienced this last week, actually, at my shop. We had 7 boards in the oven, and then the power went out, right? And then so we were able to, I think it was like a quick poof, poof, right? But enough to kick it out. And so we opened up the thing and then got to see the various failure stages, right, of all that, right? And I should have took a picture of, like, this is what happens if you stop reflow at this point.
Yeah,
but
at least get some content.
I was just too sad about it, right? And I was like, come on, like we just turned everything full automatic and, and then this happened, right? So
now, on the other side of that, we mentioned kind of leading into the conversation about when you get to the thermal profile, right, what we're seeing for trends, really it's getting more challenging, right? So especially, with a lot of this data center stuff that's going on, the AI drive that's going on, we're seeing a lot of activity in really heavy, high mass boards with large BGAs and other components that require very, very specific, tight thermal profiles. So to your point, that's where we're starting to see resolution is starting to become really, really important.
The good news is, though, when the components have those really tight restrictions that make it harder to assemble them well, they're also infinitely more expensive, too. So
they most certainly are.
We were in your booth yesterday checking out the Aurora.
Great name.
Daniels. Aurora, Nebraska. And I thought there was one thing that captured my eyes, because sometimes, there's these really big, flashy features on a machine, but sometimes it's the little things, little details. So talking about those heavy data center boards, right? Talk to us about that feature on the on the rails or the conveyor, right? Because those heavy boards are going to wear down those contact points. But you guys came up with a pretty innovative solution for that.
Yeah, so whenever you're processing these really high mass heavy boards, right, you're getting up to 20, 25 pounds or greater, right? That's always a challenge for the reflow oven. So you've got to come up with solutions. And when we look at it in a few different ways, right? So we look at it, the first thing I'm going to ask the customer is, I need the dimensions of the board, how much does it weigh, what's on it, what's the thermal profile, those kind of things. And then I back into it from there and say, okay, I need enough thermal load to handle that load as we're putting it in. So that leads back to heaters, for example, what type of heaters and how many kilowatts we need to get of heat into that board. So we kind of handle that piece, which we have solutions for. And then we move into the mechanical piece, which is the conveyor, which we talked about yesterday. And with the conveyor, depending on the loading, like, so say, for example, we have a printed circuit board, the customer says, here's how big it is, its size, weight, all these good things. Well, we look at things at like pounds per square foot of loading, whether it's the weight on the rail or whether it's the thermal loading that we need to calculate and figure out. So with the rail in particular, right, the edge rail conveyor that the board travels across on, if the density of that weight is highly concentrated on the rail in certain areas, over time, we all put hard coats and other things on the rails to get the chains to move smoothly. Well, that stuff wears off under that kind of weight. It creates friction and it causes issues. So instead of having to change the rails out, because we don't want it to be a consumable, so to speak, right? What we've done is we've come up with a solution where we basically create these wear strips. So over time, these wear strips are basically just screwed into the side of the rail. So eventually, if the wear strips wear down, the customer doesn't have to replace a rail. All they do is, an hour or so, they remove the wear strips and they put a new set in. Now, the wear strips, so far we've seen, are lasting significantly longer than the rail surfaces were. So, you don't have to change them every 6 months. It goes a much longer period.
So I know when I'm doing a selective solder job, the heavier, more copper that's in the board, the longer I need to preheat it, such to get good results on the soldering. You guys could have elected to just go with a 72-foot-long machine, but instead you just used higher wattage on some of the zones and things like that to deal with delivering the amount of heat you need in a regular oven footprint, but still being able to get the energy and the heat into across the whole board and get it properly reflowed, even if it is 20 or 25 pounds.
I mean, it comes down to, right, us reflow oven manufacturers, we all do things a little differently, right? So when we look at our heat delivery system, it's about keeping it as efficient as you can make it, right? But giving you the flexibility. We talked about figuring out how heavy is this thing and how concentrated is that weight or that mass. Well, we can figure out, all right, I need to put this much heat in the board. So between the convection rate, right, which has to be precise, right? So we got the convection rate that we've got to deal with, the set points, and basically kilowatts, right? How big do the heaters need to be? So by doing it that way, we can figure out, as you mentioned, instead of just making the oven longer and longer and longer and longer and more zones, we figure out, okay, we need to concentrate this amount of energy that's got to be delivered to the board and how much it's going to absorb. And then we figure out how many, what size heaters we need and what convection rate will work and all that kind of stuff. And that helps us keep the footprint reasonable, right?
I wonder if that same logic would apply to the 4-foot boards, because around me there's so much automotive work and there's so much running LED lights, right, that it's cheaper to just manufacture here in the States, thankfully. So all the big three come to our shop, our area, and there's a bunch of 4-foot PCBA guys around here.
Yep.
But they're all running, 150, 200 plus, inch ovens, right? The big boys. And I wonder if they could get away with it, because it's eventually you're going to run out of space in your building. I don't care what you have. You have enough automation in that thing, it's going to take up so many slots, right? I almost wonder if that would apply for them as well, because the weirdest part was, like, my buddy Weston, he was telling me sometimes that same board is in 3 zones at the same time, right?
Exactly.
And then profiling that, and then because my probe distance from like when I do a thermal profile on it, from the top part to the bottom part, right? It's maybe a little bit behind, right? But a 4 foot that's got to go through 3 different. It's quite a distance. It creates a whole nother challenge right there. So
Yeah, but we still see it. I mean, this is how we're going to process these 4 foot long boards. And, the leading edge to the trailing edge is going to have a pretty significant delta T just because, if it's heading into the reflow zone, the rest of it's still in the soak. So you've got this. And so you kind of have to think about that into the design, right? If it's a simple forgiving product, then it's less of an issue. But if you've got specific components or you're going to put any stresses embedded in the board, you got to be careful how you handle that transition.
Sometimes you're walking through a grocery store and the aisles like light up as you go. Have you ever considered that with the reflow oven? Like somehow it can only heat up when boards are present through the zones and regulate the temperature in a more efficient way.
Before you answer that, what kind of grocery store do you go to?
They don't do that around here? No?
That must be a Nebraska thing.
It's energy conservation,
Yeah, I mean, the way we deal with that, all of that, I mean, all the controls in the oven are designed to deal with what's right in front of it. For example, our approach is, and we're kind of getting into the weeds here in design, but our approach on the thermal side is to have our control system and our control thermocouple that's looking at the temperature of the zone be right in the path of the load. We don't move it out and hide from it. We put it right in the path of the load so it sees it immediately. And again, our thermal delivery system's designed in such a way where we use a low mass, very high surface area heater. So as soon as the load hits, the TC sees it, boom, the power is being applied. And it almost instantly translates onto the board. So the control system is really, really adept at, and the algorithm, the way it's written, is really adept at managing the transition from the load to no load as well. So this is kind of, it's not the light effect, but it's the control system behaving like, okay, there it is. I need to deliver more power to the zone and not allow that zone to drop in temperature and deliver the same thing over and over and over and over again.
Because that energy has got to get transferred somehow, right?
Right.
And if it's going to pull from there, then it needs to have that heater zone kick back in there, right? And I don't know. I love the new, I don't know if it's new, but it's new for me because I started with a 2006 Peermax 98 nitrogen. I got the 125A now.
Yep.
The product tracking feature on it is, I feel like that software, I don't know, it's a little bit different from the one that I had.
Yep.
Thank you, by the way, for not changing the default password. Because we were like starting
It's the
it
little
up on
things that
the
matter.
little
Well, I'm
things
telling
that
you,
matter.
if you go around to like another BTU guy and you say, hey, is your username and password this, right? We always say the same thing. We always say the same acronym, right, of
Right.
what it is, right? So it's
Yep.
just, I was like, all right, I feel at home. I know how to use this thing a little
Right.
bit. But yeah, it's just a lot of cool features that are on there, and I was always curious why does the nitrogen require a chiller for the cooling zone?
So when you move to nitrogen, I mean, as we all know, the oven gets more complicated, more hardware, and it's obvious. I mean, to me, it's obvious why, but maybe to others it isn't. In fact, I just had this conversation with a customer just before I came here about the differences between the two. And the reality is that we are now sealing everything up that we possibly can.
Yeah.
And, philosophically, most of us use room air as simple as we can for cooling in an air-only atmosphere oven. But when you move to nitrogen, you can't use room air anymore as the media. And you need to keep the cooling section gas tight so it can hold O2 levels. So how do you do that? You still have to create some kind of way to create cooling. You got to take the heat away somehow, so you go to water. So again, it makes the oven a little more complicated. But on the other side of that, you can also get better exit temperatures when you move to a water-based design, because you're not relying on temperature of the room as your water, so to speak, right? So when you move to that, you can put chilled water in there and you get a consistent exit temperature. Again, it just makes it more repeatable.
So there's pros and cons to both systems, right? Nitrogen or air reflow ovens.
Sure.
I mean, which one's right for me?
That's the question.
It's always it depends, right? That's what it always comes back to.
Yeah, it depends. It comes down to requirements, right? What are your customers' requirements on you, and do you need to run in an inert atmosphere? And again, there are inherent challenges when you move to that. You got to go to active flux management systems with nitrogen, right? The process gets a little more complicated, but at the same time,
It's not that complicated. It's
well,
2 levers and you pull out some sponges and put some new ones in, right?
I mean, the design is more complicated.
Yes, it is.
Yeah.
It is.
Sean, you made a LinkedIn post recently, and you made a statement about the reflow soldering process. I want you to say it again here so we can have Bob either affirm or dispute said statement.
So my memory is like a goldfish, right? It's my spirit animal. So I'll try to remember it. I believe I said most people think that the reflow oven solders the PCB, but it's actually the PCB that solders or something like that, or actually does the work.
I wish it was that simple. So my response to that is this, right? At least from a technical standpoint, there's a little bit of truth to both sides of that, right? So the source of the heat is forced convection. It's the oven is providing the only heat that's going to be provided that's going to be put into the printed circuit board. So it's a combination generally of 2 things. It's forced convection, hot air blowing on the top of the board and the bottom of the board, right? And that's from a surface point of view, pushing into the board, right? Typically, your lighter components, pads, things like that, are going to be easily susceptible to that. And they're going to solder fairly quickly, and take a heat gun, put it on the top of a board, and you can create the same effect. But there's the other side of it. There's the conduction side of it. The board becomes a conductor of thermal energy as well. So it's 2 pieces. You've got a heat source that's trying to provide a very uniform blanket of heat and energy to go into the board. And then the board itself has components. It's got copper in it. It's got other things in it. And it becomes a conductor of heat as well to try to become more uniform. So it's 2 pieces. It's forced convection as the source and conduction. What is the ratio between those? Depends on the board, the size, so.
What's your opinion on formic acid reflow?
So formic acid reflow.
Can I give you my perspective real quick?
Sure.
It looks terrifying. I'm not going to lie, right? Like, it's like I got to have people sign waivers, I feel like, if they have to bring this thing into my building. But I mean, the voiding looks, on the results that I've seen, looks pretty good. But, all right, sorry, go ahead.
No, that's okay. So, we're exploring formic acid as well and other types of fluxless, so to speak, processes. And where it hits us is really in our semiconductor packaging business. We've got a significant amount of market share in that area in Asia, and this is a very hot topic. So it has its place, right? It's been around for a long time, and it has its place. But what we're also finding is that depending on the customer and how sophisticated that customer is, the formic acid does deliver on what it says, but it can also leave things behind. It can leave residues behind and things like that. So depending on the customer, those residues may or may not be a welcome addition to their product, right? Their high value product. But there are other solutions as well that can produce similar results. For example, plasma is another option that others are looking at, right? To see if that is a way that you can eliminate any extra bits you want to put on the board after.
Yeah, even if you can't necessarily remove all of them through plasma, sometimes that can make them benign and inactive and inert.
Correct.
And
that's right.
safe to coat over or use or whatever.
Yeah, so the question is which one is going to win, or are they both going to be available? I mean, both of those technologies are in the market. They've been around for a long time. It's just putting them together in such a way that it works for customers, right?
Absolutely. Well, this has been educational for me, I know. I always want to fill that void in my knowledge, which I feel like is reflow. I don't talk about it nearly enough since my process is kind of in the beginning, but
Way to use void.
We just blame you anyways.
absolutely. Well, people say 80% of defects are a result of the screen printing process. I say 100% of them are a result of reflow because it's not a defect until you set it in stone.
That's right.
The best one I heard was 80% of defects are caused by SPI marketing people or something like that. Yeah.
Well, Bob, thank you so much for joining us and for your time. How can people find BTU, see what your latest offerings are, and get in touch with you?
Yeah, so you can visit us here at the show at booth 1800. We've got we're showing off our new Aurora platform. We've got a 12 heated zone oven there. We're showing off our Aqua Scrub technology, which is really cool, very effective flux mitigation technology. We've got some other stuff in the booth as well. We've got some new things we're doing for the customer on the parts and support side, e-commerce, and things that we're working on to make it easy for customers to do business with us. So yeah, those are the key things. You can find us obviously at btu.com as well.
Awesome. Well, thank you for joining us, and thanks for tuning in.